In the last video we discussed sequences. In this video we're going to pick up right where we left off, but we're going to start to join these sequences with addition. What we're going to be looking at called series or infinite series. Quite simply, an infinite series is the sum of infinite sequences of numbers. So again, remember we defined, we would have a formula for a sequence, say just a simple thing like n. Well then, an is equal to, a1 is equal to 1. A2 is equal to 2, A3 is equal to 3, and so we could write this sequence as 1, 2, 3, and just keep going. Now what we're doing is we're saying, well, let's build a series. Let's put sums between these now. Let's add them. So it's no longer a sequence, it is a series of us adding together these numbers of these sequences. Now, it's going to be hard to define this in terms of a formula as we had before, because we can see that these numbers just keep growing and growing and growing, and there's not an easy way to write that until we get to our summation notation, which we will do. But what we can do to begin to get an idea of what things going to look like, to try to get a formula down on our paper, is to look at some of the terms. We can begin to understand a series by looking at its first few terms. It's kind of the same thing I did above. I was trying to get you guys the idea of what a series is, so I took the first three terms of just the an equals n sequence and I added them together. What this is called, this gives the partial sum. And we can define the partial sum for the first n terms as S sub n. So what I want to do is I want to take an example using this to try and get an idea what's going on with a series. I want to take the series 1 plus 1 over 2 plus 1 over 4 plus 1 over 8, and I want to look at its partial sums. Let's find the partial sums. And let's start by finding the first partial sum. And I made a mistake here, and this is a good learning lesson. I put pluses between these, and I said I was giving you a sequence, and that's not a sequence. If there are pluses between these things, that is in fact a sum. These need to be commas right now. And so then once I put the pluses between it, that is what turns it into a sequence, a series. So right now this is a sequence. We want to look at the sum, meaning we're going to begin to look at the series. So the first partial sum means I am looking for Sn, which is S1, which is just the first number in the sequence, which is equal to 1. Let's find the second partial sum, which means we're looking for S2, which says we're going to take 1 plus 1/2. It'll give us 3/2. Then we're going to find the third partial sum, and that would be equal to S3. Let's box that. S3 would be equal to 1 plus 1/2 plus 1/4. So we could write this as 1 3/4 or 7/4. Right? Either of those would be correct. And we can do this for as many as we want. But what we want to begin to understand is what will the nth term look like. So what are we adding each time as we go along? What about the nth partial sum? So we're starting with 1, then we're adding 1/2, then we're adding 1/4. So what are we adding each step along the way? Well, these numbers are equal to 1 over 2 to the n minus 1. We had 1 is just 1 over 1, or 2 to the 0. Then we had 1 over 2, 1 over 4, 1 over 8, 1 over 16 would be the next one. We can see the pattern. So each time this n is getting bigger by an exponent, we had to start at n minus 1 because the first one was just the whole value of 1. And so let's see if we can come up with a value for this. What is this going to be equal to? Well, what this is going to be equal to is 2 to the n minus 1 over 2 to the n minus 1, all in the exponent. Or we can express this as 2 minus 1 over 2 to the n minus 1. So what we want to begin to think about is, where is this going to? What is this sum going to approach as that n gets bigger and bigger? So once again, we're going to apply limits to these. Let's take the limit as n goes to infinity of 2 minus 1 over 2 to the n minus 1. That's simply equal to 2. So somehow, this initial sum right here, the 1 plus 1/2 plus 1/8, when we add all these things together over and over again, that is going to 2. And let me give you a way to kind of visualize that. What we saw at first is that the very first partial sum, we had 1. And then that next term, let me call it A1, that next term we had another 1/2. So this was 1, this A2 is equal to 1/2. Then we had a quarter. Then we had an eighth. And what we can see is just each time we're going to be taking half of what we had. So if we just keep taking half, we're adding the rest of that 1. The rest of that 1 is getting added right there. And that is where we are getting that 2 from. So that gives us the visualization. So let's define very formally an infinite series given a sequence a sub n, the expression a1 plus a2 plus all the way up to an, and then beyond, I shouldn't end there, but plus however many terms we have is an infinite series. Infinite series means we don't stop at just the n, we just keep going on through. Once we have those infinite series, what we have to do is we have to look at their sums. Just like we did in the example above, where we looked at the 1 plus 1/2 plus 1/8 plus 1/16 and so forth. In order to see what that series is really doing, we need to look at the sum. And so the sum, partial sum S1 is equal to A1, partial sum S2 is equal to A1 plus A2, partial sum S3 is equal to A1 plus A2 plus A3, so forth, all the way till we get up to the nth partial sum, where we're adding those first n terms of the sequence. We can write that more concisely using summation notation. We're going to use this summation notation for these series because that's a very concise way of writing them. We can write the summation from k equals 1 to n of ak. They form a sequence summation of partial sums. We have a sequence of partial sums, the curly brackets Sn. So what we're doing is we're looking at those first partial sums to actually form a sequence so that we can better understand what is happening with our series. We understood sequences very well, we knew how to work with them, so by turning the sequence, or the series, by looking at their first terms, turning that into a sequence, we can study the series. If that sequence of partial sums converge to limit L, we say the series converges and its sum is L. That is like the example we did with the 1 plus 1/2 plus 1/4 plus 1/8, so forth. And we would write that limit as n goes to, or let me write it a slightly different way. We could write the summation from n is equal to 1 to infinity of an is equal to L. So that summation as we go off to infinity is equal to L. If the sequence of partial sums does not converge, we say the series diverges. So to consider the series, because these things go on to infinity, because they keep going on forever and ever, we have to look at a certain number of those terms. We look at those first n terms, we think about what's happening there. That picture, and when we look at that picture, we can create that new sequence. We're creating a sequence of sums. So then we can talk about that sequence as we did in the last unit. We can say, well, that sequence converges or it diverges. And if it converges, we can actually get the sum of the series. However, if it diverges, something like the first thing I showed you where we had just a sequence an is equal to n, we're adding all those terms together, well then we'd have 1 plus 2 plus 3 plus 4. That is going to diverge, and we clearly can't get the sum for that. That thing is just going to continue to grow larger and larger. So then the question becomes, how can we easily determine whether these sequences converge or diverge? This is going to be the challenge. It's not going to be so easy. So we're going to have a few different tests, several different tests in fact, to help us determine whether series converge or if they diverge. And that's what we're going to be studying for really the next few videos, several videos.